Hello, I'm Amy Lin from Princeton High School, and I'm very excited to share my project predicting compound melting temperatures from computationally derived properties using machine learning. Melting temperature is a fundamental material property that is used in many fields, such as engineering and designing structural materials for cars, planes, buildings, and more. However, the existing experimental methods to measure melting temperature are costly, dangerous, and time consuming. As a result, only 10% of around 200,000 known inorganic compounds actually have determined melting temperatures. So we turn to computational methods. For example, one of them is density functional theory. DFT can be used to predict material properties at absolute zero temperature, but it can't be used effectively for temperature dependent properties such as melting point. If melting temperature can't be calculated directly, can computational models be used to predict melting temperature? And which material properties are relevant to melting temperature prediction? We see here a few graphs of a compound's material property, such as the bulk and shear modulus versus its melting temperature. These relations don't seem to be strictly linear, and there may not necessarily be a function of best fit through these plots. So how do we tackle this? Here's the basic methodology. I retrieved datasets containing chemical compounds and their melting temperatures, their compound properties such as cohesive energy and bulk modulus, and element-based properties such as the average atomic radius of the elements in the compound. Then I built a machine learning model to predict the compound's melting temperature based on these material properties. So going into more detail here, during data preparation, I divided the compounds into 6 compound groups based on the elements they contained, either metal, transition metal, post-transition metal, halogens, chalcogens, and alkaline earth metals. I also performed data augmentation by creating extended features that are the pairwise multiplication of original material properties. For example, one of these extended features would be the multiplication of average atomic radius times bulk modulus. For training the machine learning models, I used a random forest regression model, and I used the mean percentage absolute error as the error metric. So I trained different models. There was a model for all compounds and a model for each separate compound group mentioned before. And each of these model types was trained using only original material properties, as well as using both material properties and extended features. Lastly, I also changed the choice of hyperparameters, the number of decision trees and the maximum depth of each tree, which basically changes the model structure and therefore the complexity, and I wanted to determine the optimal hyperparameters. Here are the main results. So the optimal hyperparameters turned out to be 50 decision trees and a maximum depth of 10, and this was based on the model trained on all compounds. When training separate models for each compound, it did improve the accuracy on average, especially for metal-containing compounds. For example, look at the bottom blue line on both graphs. This blue line represents the error for the metal compound group, and the error was actually reduced by about 5% relative to using one model for all compounds. This is the graph of actual versus the predicted value of a melting temperature, and it's linear, showing that the model performed well. This table shows the error of each machine learning model. Overall, separating materials into compound groups decreased this error. For example, look at the first 2 rows. The model trained on all compounds had a 20% error versus the metal compound group, which only had a 15% error. Training on both material properties and extended features also improved the accuracy. For example, look at the halogen compound group. While training with material properties only, the model achieved a 22.3% error, while it dropped to 18.7% error when I added extended features. Interestingly, the exception to both of these results was the chalcogen group, who had a higher error than the model that was just trained on all compounds, and also it did not help when I added extended features. Using the feature importance metric, I found the most important features for melting temperature prediction, and these graphs are for the model trained on all compounds. So when training with only material properties, we can see the graph on the left, that the top 5 features are the bulk and shear moduli, formation energy, mean atomic radius, and mean rho. And on the right here, we can see that when training with both material properties and extended features, This actually shows the top 20 out of 231 total features on the right. Nearly all of them are extended features that jointly use an element-based feature and the average number of valence electrons in suborbitals, particularly the f suborbital, which is very, very interesting. So overall, the machine learning models, specifically RFR models, predict melting temperature with promising results. And the compound group specific models gave a higher accuracy for metal, transition metal, post-transition metal, alkaline earth metal, but not for halogen and chalcogen groups. And if you looked at my slides before, in the second half of my slides, I have some additional figures, and they show that for metal-containing compounds, the energy-related properties and electronegativity-related properties are most important. The joint use of material properties, meaning just using extended features, as well as the material properties, improve the prediction accuracy for all groups except the chalcogen group, which I mentioned before. And the most important extended features jointly use the average f suborbital valence electrons and an element-based property. Thank you for your time.